Hi, I'm Bill Manry with Amdahl Corporation, and this is a technical presentation on VSAM performance considerations. If you haven't read the glossary material yet that was provided with this videotape, you might want to take a look at it before we get started because we rely very heavily on some technical terminology that's defined there. This is an MVS-oriented presentation. We're going to concentrate our attentions on KSDS and alternate index type structures because they have the most complex tuning considerations. We've also included considerations for the new Data Facilities Extended Function product from IBM. That product creates a new type of VSAM catalog. It also introduces some minor changes in the tuning considerations for VSAM clusters. The presentation breaks down into two sections, basically. We have the bulk of the material, which is a discussion of the parameters that are coded in an IDCAM's define or alter command for a VSAM cluster. Following that, we have a section on execution time parameters, which is essentially a discussion of VSAM buffers and how they're allocated and how they affect various types of VSAM access. Now, the presentation is color-coded, and you'll find that we have recommendations that appear in black and usually have a box drawn around them. Following that, in green, will be an explanation of how or when that recommendation is of benefit to you. If there are implementation issues or a variety of techniques, those are usually described in blue. And then finally, and very appropriately, if there's any warnings, if there's any caveats or special considerations in using this recommendation, those will appear in red. Now, in the define and alter parameters section, that breaks up into three subsections. We look first at the parameters that influence the amount of space used by VSAM and the allocation techniques and the way volumes are managed. Secondly, we'll look at the parameters that influence the logical and physical structure of VSAM data relative to DASD devices. And then finally, we'll look at define and alter parameters that have an influence on VSAM's processing behavior, although not necessarily the physical structure of the VSAM data itself. Moving right into the recommendations then, first of all, you should use cylinder-oriented allocation for the data component of your VSAM clusters. This is a recommendation that originated in non-VSAM where cylinder type allocation was recommended. The reason for this is with cylinder allocation, an access method can guarantee that a data set ends on a cylinder boundary, which permits that access method to use actual multi-track channel programs without I/O interrupts to verify extent information. With VSAM, the processes that will benefit from cylinder-oriented allocation include sequential retrieval and CA splits when you provide additional data buffers. Also, the output of a control interval that begins on one track and ends on another, that's a CI that spans a track, and the process known as a CA pre-format. Those are also multi-track operations that benefit from cylinder-oriented allocation. Now, to achieve cylinder type allocation, the easiest way is to simply code the cylinders parameter either at the cluster or AIX level of your define or at the data component level of the define. Either way, you do get cylinder-oriented allocation. Additionally, you can use the tracks or the records parameter in your define command, again, either for the cluster AIX or at the data level. And if the values you specify convert to more than a cylinder on the device involved, then VSAM will convert that allocation internally into cylinders, and you have achieved this recommendation. The only warning that goes with this recommendation is with cylinder-oriented allocation, your data component CA size will be a cylinder. Usually that's desirable, but there are occasional circumstances where you want to manipulate CA size to be something other than a cylinder, and so this recommendation should be avoided in that case. Next, we recommend that you keep your VSAM components within one single primary allocation extent. This is of value for several reasons. First of all, it reduces DAS defragmentation. VSAM has some very powerful secondary allocation capabilities, and clusters can spread out all over a volume and cause serious fragmentation problems. By keeping those components within a single extent, you reduce fragmentation. That's good not only for you, but for other users of the same DASD volume. Also, by reducing the number of secondary allocations, you'll reduce the amount of seek activity involved in accessing that VSAM data. When you have secondary allocations, the allocation pieces themselves can occur anywhere on the volume, which generally implies a spreading out of your data and increased seek activity. Finally, doing secondary allocation with VSAM means calling EOV, and that in itself involves many CPU cycles and I/O for catalog updates, etc. So there is overhead associated with secondary allocation that'd be very nice to avoid, particularly for online applications. So by allowing adequate space in your primary extent, not just to contain your records, but to allow for expansion of that cluster, you'll avoid those secondary allocation calls and you'll enjoy a general performance savings. Now, achieving this recommendation is a rather complicated thing. You have basically two avenues of approach. First of all, you can calculate your space in actual DASD device terms, and you can code the space parameter then in either tracks or cylinders. To do that, you have to factor in several things. The arithmetic itself is rather complicated. First, you take your average size logical record and you figure out how many you can fit into a control interval, allowing for things like control interval definition field and record definition fields that have to be present. Additionally, you have to factor in free space if you're going to allow free space in your cluster. You also have to consider how your CIs and CAs are going to map physically onto the device that you're using. If your CI has multiple blocks, you have to consider that. Also, you have to consider options like embed that influence the size of the data component structure. And finally, and kind of the main point of this recommendation, you must also factor in those anticipated CA splits, the amount of growth that you expect your cluster to have. Now, in spite of all this, in spite of your best efforts, it may still be impossible to achieve this one extent allocation. For one reason, VSAM can satisfy an allocation quantity in up to 5 pieces. So depending on what space is available on the volume, you may not be able to avoid these multiple extent situations for your cluster. But with a little careful choosing and with monitoring of DASD space, you can achieve this recommendation and avoid those secondary allocation calls. Now, there is a slightly easier approach to dealing with this situation, and that is to use the records parameter in your define command to specify the amount of space. If you're going to use records, there are several things to consider. First of all, you probably want to specify it at the data component level. That's where it's the most meaningful. Secondly, you want to think about the fact that VSAM still does not, in fact, consider the free space percents. If you're going to have non-zero free space percents, then you're going to have to factor them into your estimation of the values for the records parameter. Additionally, you're going to have to put an accurate average record size in the rec size parameter because that is the basis of the space calculation when the records parameter is used. I do note on here you can still achieve cylinder-oriented allocation using the records parameter if the values that you specify convert to a cylinder or more of the device involved. Now, we said to do that for the data component. What about the index component? The index component has an internal structure known to VSAM but not necessarily known to you. And it turns out that given an accurate estimate or calculation for data component size, VSAM define processing will do a very accurate job of calculating the index component size. And he knows to take into considerations parameters like embed and replicate that influence the size of the index. So the recommendation there is don't code space for the index component. Code it only for the data component and allow IDCAMs to calculate an amount for the index component of your cluster. Now we move into the free space parameter, and first of all we have kind of a general recommendation, and that is to consider free space percents on the basis of the type of additions you're going to make to your cluster, not just the amount of inserts, but the type of inserts you're going to be doing. If you look in the VSAM Programmer's Guide, you'll find a formula in there for calculating free space percents for a VSAM keyed cluster. The problem with that algorithm is it assumes that you're going to be doing direct inserts and that they are randomly and uniformly distributed throughout your cluster. Well, that doesn't describe very many real applications, and in addition to that, VSAM has a variety of fancy techniques for adding records to clusters. So in looking at your own particular application, you have to consider the techniques that you're using to add records when you consider what you're going to code for the free space parameter. The objective, of course, is to choose values that reduce CI and CA split activity, but don't over-allocate so much free space that you have wasted DASD space. Now, looking at the access techniques that are available with VSAM, consider, first of all, direct inserts that are well distributed. In that case, you are safe using the formula in the Programmer's Guide. That's an empirical calculation, and it gives you a good value for free space. If you're going to use a technique like sequential insert, which is sometimes called a mass insert, your choice of free space really depends on what your subsequent insert needs are going to be in the area where you're adding records, because sequential insert is not going to use any free space presently in the cluster. Rather, it's going to create new CIs and CAs that have free space in them. So you want to choose a free space value very carefully prior to doing sequential insert processing. When you use the skip sequential insert technique, turns out the considerations there are the same as for a regular old direct insert. So again, you might be safe with the formula that's in the Programmer's Guide. And finally, if you use the ACB macref equal SIS, that's the sequential insert strategy used during direct processing, the free space considerations there are the same as for a sequential insert, meaning the areas where you're inserting don't have to have any free space. What you're really concerned with there is how much free space is created in the areas where you're adding logical records. Now let's make sure we understand how the free space parameter works. Free space is really just two numbers in the VSAM catalog for a VSAM cluster. So the real trick in understanding this lies in how or when are those numbers interpreted. And in so doing, we look at the various types of access again. When you're doing sequential loading of a cluster, that is like an initial load, or extend processing where you're adding to the logical end of a cluster, VSAM will observe the free space percents. That means that VSAM will use those percents to determine when to stop loading a CI with records or loading a CA with CIs. That means you're creating free space. If you use sequential insert, or you use macref equal SIS, the sequential insert strategy, we get a slight variation of that behavior in that VSAM will utilize fully the first CI and CA that insert hits, but as that process begins to create new CIs and CAs, VSAM does observe the free space percents and will create free space in all new CIs and CAs. Finally, our good old direct insert, or record lengthening, which is a special class of direct insert, those processes will utilize free space for the addition of new records. An additional point to be aware of here, by the way, is that direct insert or record lengthen can cause CI and CA splits. And after a split, the CI or the CA has about 50% free space in it. So the direct insert process does allow free space. It just doesn't give you very much control over it. Now, in a lot of applications, you're going to find that you have mixed processing sequences. You may do some direct updating, you may do some sequential insert, and so in those cases, you're dealing with mixed techniques, and you're going to have to possibly vary your free space from one execution of a program to another. Now, on the graphic here, I've illustrated an example which shows a user first defining his cluster with free space 30, 15. That's a pretty good allocation of free space. Following that, he executes his initial load, which is a sequential process, probably with a repro command. Now, since that's sequential, VSAM does create 30% and 15% free space in the CI and CA respectively. So we have created a cluster that contains free space. Now we can execute a direct update, meaning direct inserts of records or lengthening of records, and we will utilize the free space that was created during this initial load. Now at this point, we might want to execute a sequential insert. And in this particular example, we alter the free space to 0, 0, and then run the sequential insert. Now, this altering of the free space to 0, 0 means exactly one thing. It means the CIs and the CAs that are created by this sequential insert are not going to have any free space in them. The only reason we'd want to do that is if we know that we're not going to insert records into the areas that we're adding through this mass insert. Finally, we can come around and issue another direct update, and in this case we would hope that our updating would only hit the areas that we loaded initially up here, because that's the only areas in our cluster that have any free space at all. Finally, it's very typical in applications to have a cluster, some areas of which are inserted into very heavily and other areas that don't receive any inserts at all. We refer to those as localized or concentrated inserts. Now, you might be tempted in that situation to define and load your cluster with big globs of free space everywhere just to accommodate that high insert area. It turns out that there is a technique for varying the amounts of free space through your cluster, as we've illustrated here. In this example, we've defined our cluster with free space 0, 0 and then issued a repro to initially load a set of records in. In that case, we've created a cluster that has no free space at all, and obviously that's the area where we don't anticipate having any insert activity. Now we come in and we issue an alter of the free space values to 3025. Keep in mind that only changes the information in the catalog. But we follow that with a subsequent repro using a different input file. This is the next sequence of records that go into our cluster. Obviously, this is our high insert area because as we sequentially extend the cluster with this repro, we create CIs and CAs that have 30 and 25% free space, respectively. Finally, in this example, we alter free space back to 0, 0 and repro extend the remaining portion of our file in. That's the in file Z part. And again, that's an area that contains or in which we anticipate no insert activity at all. Now, you can vary this technique according to where you anticipate you having inserts and how many of those you expect. But the general concept is to intersperse repros and alters of the free space to create areas that contain the amount of free space that you need. Now, a question that I'm very frequently asked is, should I use unique or suballocate VSAM clusters? If you're not using DFEF, then I believe you should use suballocate because that gives you access to the full range of VSAM functional capabilities. For example, when your cluster is suballocated, you can manipulate your control area size. With uniques, your control area size is always one cylinder. Now, one cylinder is usually a good CA size, but there are circumstances where you want it to be something other than a cylinder. With suballocates, you do have that capability. Also, when you have suballocate clusters, if you perform secondary allocation, VSAM end-of-volume processing will not have to invoke DADSM, who's the guy who updates the DASD VTOC. Suballocate clusters space is managed totally within the catalog, and therefore VSAM EOV for suballocate clusters is quite a bit faster than for uniques. Also, with suballocate clusters, you can have up to 123 extents per VSAM component. Now, that may sound kind of extreme, but it's certainly a great improvement to be freed from the 16 extent restriction presented by uniques or, of course, presented by non-VSAM things. Finally, with suballocates, you can use reusable VSAM clusters, and that is a desirable capability. When a cluster is reusable, you avoid the overhead of having to do a delete and redefine of that cluster every time you want to reload records into it. Now, there are definitely some warnings that go with using suballocate. For example, your space management for DASD is going to become a little more complicated. Somebody has to define data spaces, first of all. Second of all, if you have billing or accounting practices or procedures that are based on DASD VTOC information, when you start using suballocate, there won't be any information in the VTOC for those procedures. Instead, the information is contained wholly within the VSAM catalog. Another point is if you use reusable clusters, which are available with suballocate, you are limited there to 16 extents, sort of like with unique clusters. And then finally, and this is probably the key point in this day and time, if you intend to migrate to the Data Facilities Extended Function product, with that product, all VSAM clusters are going to be uniques. In that case, it may not be desirable for you to use suballocate clusters because it's going to further complicate your conversion to the DFEF product. Next, we get into a performance technique called separation of data. The basic idea is take the data of your VSAM cluster and spread it across DASD volumes and hopefully across physical paths, that is, channel and control unit access paths to those DASD. This is of value to you when you have multiple requests active concurrently, which generally is a reference to online applications where multiple terminals or transactions can be accessing a cluster at the same time. With the DASD separation technique, you can have multiple I/O operations actually taking place at the same time, so you have overlapped I/O operations. An additional benefit that can be realized when you dedicate volumes to the pieces of your cluster is a reduction of seek activity. Since each volume has less of your data on it, there's a smaller expanse to be seeked over, assuming that you're not accessing any other data on that DASD volume. Now, there's a variety of techniques for achieving this multi-volume allocation with VSAM, and there's definite pros and cons involved in these things. Looking here, the simplest technique and the one that most frequently occurs is simply specifying multiple volumes at the cluster level of your define command. This commonly occurs when the cluster itself simply won't fit on one volume and multiple volumes are required. The problem with this technique is VSAM simply fills up the first volume as far as he can with as many secondary allocations as possible, and only when he can't perform any further secondary allocations will he start to slop over onto the second volume. The same story occurs there, and then finally to the third. When these are not in use, they're referred to as candidate volumes. The problem with this technique then is that you have very little control over how much of your data goes on each volume. So it's, from the performance standpoint, it's not a great separation technique. Now, a technique that offers a little more control is called data and index separation. That's where the volumes parameter gets specified individually at the data and index component levels, and that causes VSAM to store the data and index component on separate volumes. Again, there's a limitation to this technique. If you've tuned your cluster well and you know how to allocate your buffers, you're probably not accessing that volume very much that contains the index component, and therefore separating it from the data component volume isn't going to buy you very much at all. So that leads us to the really powerful technique for multi-volume allocation, the key ranges technique. In this example, we show a define cluster command, and for the data component, we've coded multiple volumes, again V1, V2, and V3. We've also specified 3 key ranges and the ordered parameter. The ordered parameter tells VSAM that there's a one-to-one relationship between key ranges and volumes, and it causes VSAM to allocate space individually on each volume. And on the first volume, records whose keys are in this range are stored. Second volume contains records in this key range. The third volume contains records in this key range. If you choose these key ranges judiciously, you can divide your cluster up into equal-sized segments, and you don't have to have 3. Obviously, it can be 2 or it can be 10. And that way you have your data evenly distributed over multiple volumes, and you get the maximum benefit of the multi-volume allocation technique. Now, there's definitely some warnings that are associated with multi-volume allocation also. First of all, multi-volume allocation is complicated and requires planning. It's not something that you want to undertake under any kind of trivial circumstances. In particular, your catalog and cluster backup and recovery issues are complicated by having multi-volume data sets. For one thing, if you do volume-oriented backup and restores, having multi-volume data sets means synchronizing all backup and restore activities so that you don't have one piece of a cluster out of synchronization with other pieces of that cluster. Another point, this is true with all multi-volume techniques, on each volume that VSAM uses for a given component, the primary space quantity from the define command will be allocated first, followed by secondary allocations. That means if you have 3 volumes specified and maybe 20 cylinders of primary space, you really have 60 cylinders of primary space because each volume is going to get 20 cylinders allocated on it for the first allocation. Then each subsequent allocation on each volume will be your secondary quantity, whatever that is. Finally, with the key ranges parameter, a very specific warning, the key ranges themselves are actually enforced by VSAM. That means that if you insert a record to a key range KSDS and the record's key doesn't fit in any key range, VSAM will reject that insert request and give you a logical error feedback code. So that means you want to pick key ranges that will accommodate all of your records. Note that key ranges can be expressed in hexadecimal or binary or character notation, so you can accommodate any possible key that can occur. Now we move into structural parameters, and when we talk about structural parameters, we're really referring to things like CI and CA sizes and options such as embed and replicate that influence the behavior of the index. We're going to focus first on control interval sizes for the data component, and we're going to look in particular at direct or random type applications. The recommendation there is to choose a data component CI size that is small and is stored as one physical block. And that means your good choices are sizes such as 1024, 2048, or 4096. First of all, an important concept here that was true also with non-VSAM, in a random application, you want the piece of information that you transmit back and forth to the storage device to be small so that you don't have a lot of wasted data transfer every time you access a single logical record. That was true with non-VSAM block sizes. It's also true with VSAM control interval sizes, since the control interval is the unit of information that is physically read and written to DASD. VSAM never processes less than a whole control interval at a time. Having CIs that are recorded as a single physical block is also an advantage because you avoid the overhead that's associated with interblock gap information, and you avoid the possibility of having a control interval that spans a track boundary or maybe even a cylinder boundary, which will introduce unwanted seek activity or possibly I/O interruptions. Now, when you're choosing a CI size for a direct application, your choice is mitigated, first of all, though, by your logical record sizes. You want to pick a small data CI size that's small relative to your logical record size. You want a data CI that will contain a few logical records, not a huge number of them. Something to be aware of is that things can happen during the define process that cause your data CI size to be changed automatically by VSAM, even if you specified a value. For that reason, we recommend doing a list-cat all after you execute your define to determine what the precise result was. In particular, when you make reductions in your data CI size, it tends to cause an increase in your index CI size. It won't always, but it depends on certain internal threshold values. And you can see suddenly very radical increases in index CI size when you make data CI size smaller. That's one thing to look for in this list-cat all. And secondly, in general, during the define process, VSAM may override your specified data CI size value because of the influence of other parameters, and therefore that list-cat all enables you to check and ensure that VSAM didn't do anything weird to your data CI size during the define process. Note that those changes are not signaled to you in any way during the define. There's no warning message or anything. So you have to look at that list-cat all to make sure that things didn't get changed that you had actually specified. Now, in looking at a sequential application, the considerations again are similar to those for non-VSAM. If you remember, probably for QSAM or BSAM type access methods, the recommendation was always to choose a large block size and reduce the number of I/O operations. The same is true with VSAM control interval sizes. In a sequential VSAM application, you probably want to pick a data component CI size that's a multiple of 4096. That's because 4096 is the largest physical block size that VSAM will use, so you minimize the number of physical blocks. The large CI size reduces I/O operations for each get or put, because with sequential access, the access method knows that if you requested one record out of a CI, you're probably going to request the next and the next and the next. So many records can be returned to you after a single I/O operation. One warning that goes with that: if you're increasing the data CI size for an existing application, you are of course going to see an increase in the storage required for data component buffers. Now, one tricky question that comes up is, what if you have mixed processing? What if you have a cluster that accesses both random and sequential? That's very common, as a matter of fact. The recommendation I have there is to optimize that application for random access. With sequential access, you can choose a large CI and get efficient processing, but your direct application is still going to have to ship an entire data CI back and forth, and you're going to have wasted data transfer over the channel and the overhead in real time that's associated with that data transfer. If you optimize that application for direct access, then you're going to get the efficient direct access, and you can still have good sequential performance by using multiple data buffers and getting what is called chained I/O in the read-ahead process. We'll talk about that later on in the section on buffering. Now, some general caveats that go with the issue of specifying or manipulating data CI size. We show those here. First of all, you can default your data CI size, not specified in your define command at all. I don't recommend that because IBM's default calculation for data CI optimizes the number of bytes stored on a DASD track. It does not optimize the access speed. The other thing to be aware of is there are those defined parameters that can exert an influence on your data CI size. In particular, record size and buffer space. Out of record size, VSAM will look to ensure that your maximum record size is containable within the data CI size that you specified. Specifically, the record size, the maximum record size, plus 7 must fit within data CI size unless you're using the spanned attribute. Secondly, the buffer space parameter. If you've coded a buffer space parameter, the value you specified must be sufficient to contain 2 data CIs plus 1 index CI. If that isn't the case, VSAM will manipulate these data CI sizes without warning, and therefore you'll have something other than what you requested. That's a good reason for doing a list-cat all anytime you issue a new or modified define command for a VSAM cluster. Next, let's take a look at the control area size for the data component of a VSAM cluster. The recommendation here is choose a control area size such that you do not have embedded cylinder boundaries, or stated another way, ensure that the cylinder boundaries of your DASD device fall on control area boundaries rather than in the midst of control areas. The advantage to this is that operations within the control area, in particular multi-tracked or chained I/O operations, will not encounter a cylinder boundary, which implies an I/O interrupt and it implies a one-cylinder seek, which is definitely not desirable in an I/O operation. The activities that we're talking about include CI splits, CA splits, and the general process of sequential retrieval. All of these will go faster and with fewer interrupts when the cylinder boundaries occur on the CA boundaries and not embedded within the CA. Now, the trick to this recommendation is where in the world does CA size come from? It's not an explicit define parameter. It turns out there is a way to predict the CA size of your cluster, and we illustrate the technique here. Basically, if you're in a non-DF-EF environment and your cluster is unique, your CA size is going to be one cylinder. That is always true. In all other cases, the CA size is chosen to be the lesser of 3 numbers. P plus I, which is primary allocation amount, plus 1 if you're using embed, the secondary allocation amount, plus 1 if you're using embed, and the cylinder size of the device. Now, what this really says is your CA size is never going to be more than a cylinder, and if your primary or your secondary allocation quantity is less than a cylinder, then the smaller of those two values will be your CA size. Of course, if you don't specify a secondary allocation quantity, that doesn't take place, and of course you do have to allow the one track for the embed option if you are using that option. Now, that makes this recommendation fairly easy to implement. You know the cylinder size of your device. By using a parameter like tracks for the space allocation, then you can manipulate your control area size. The only place where you run into difficulties is on the 3330 type disk drive, where you have 19 tracks per cylinder. 19 is a prime number, which means that the only CA size that meets this recommendation is 19 tracks, or one full cylinder. Next, let's take a look at the index component for a minute. For performance considerations for the index component, all we're going to talk about is the index control interval size. Control area size doesn't have any effect on the index component, and we don't have to be concerned particularly with different processing modes. Tuning the index component is easy. You want the smallest index CI that you can have that will still work, and thereby minimize the amount of data transfer, the amount of storage required for buffers, etc. Taking a look at the diagram here, you can see there's a relationship between the contents of an index CI and the data component. Specifically, we have a data CA right here, which has some number of control intervals in it, and we have an index sequence set that is a lowest level CI in the index component. The index CI contains control information and header information of a fixed size, and it contains a series of index entries that are of an unpredictable size because those index entries contain compressed keys. But there must be at least one of those entries for each CI here in the data component CA. Now, that sounds like it places a rather difficult burden on you in calculating index CI size. But it turns out there's a fairly easy way to deal with that. VSAM performs checking automatically at the time you define your cluster to ensure that the index CI size that you specified is enough. Specifically, index CI size is estimated using the algorithm that we've shown right here. Index CI equals 31, that's the header and control information, plus 8 times C, that's 8 bytes per index entry, plus 2 times the square root of C, that's 2 bytes for these things that are there called section headers. C, of course, is CIs per CA. So even if you've specified an index CI value, if the value VSAM estimates is larger, VSAM will override your index CI size with the value that he thinks is appropriate. Therefore, if you specify an index CI size of 512, which is the minimum, it ensures that VSAM gives you the minimum possible index CI size, and that's what you want for performance. The only warning associated with this recommendation is there are occasional sequences of records wherein the index entries don't compress very well, and this algorithm comes up being a little low compared to what you'll actually experience. In those situations, your VSAM cluster will take CA splits prematurely because the index sequence set record will run out of room for index entries before all of the CIs and the CA are occupied by records. There are 2 ways to detect that problem. One of them is monitoring for an RPL feedback code of 16 paired with return code 0. You can only do that if you're programming in the assembly language. The other is to monitor your cluster's space consumption behavior. And in general, if you're experiencing this problem chronically, you'll find that the cluster takes up more space than you anticipated, particularly if you've performed your space calculations carefully. Now let's take a look at the embed option. Embed is a guaranteed payback, and so we have a fairly blanket recommendation. Specifically, always use the embed option if your data component CAs are 5 tracks or larger in size. Embed's going to buy you a reduction of seek activity during sequential access when only the index sequence set records are accessed. It keeps VSAM from having to access the physical index component at all. And during direct access when you use it in conjunction with heavy index buffering. Again, in this situation, you can avoid accesses to the physical index component at all, and that can mean a substantial reduction in seek activity. Additionally, since embed devotes an entire track to the sequence set record, you can experience reduced rotational delay when the sequence set records are read, because VSAM will write multiple copies of that sequence set record on the track, and then when reading, will read a non-specific record from the track. He doesn't care which one he gets because they're all the same. Now that sounds very similar to the replicate option, which is the next thing we discuss. However, with replicate, we don't have a blanket recommendation, so pay attention to this very carefully. Replicate should be used only when you can't give heavy index buffering. Replicate gets you reduced rotational delay during operations that are going to access the index component, which means a direct get or put, or a sequential point, which also involves an index search. The point here is that when you can provide full index buffering, you don't access the index component at all other than the sequence set records. So replicate, which gives you faster access to those index set records, doesn't buy you anything when you aren't accessing those index set records. The time you need to consider replicate is when you can't provide the full set of index buffers, and that is most commonly when shared resources are used. Now, most people aren't writing their own shared resources programs, but CICSVS and IMSVS both use shared resources. Therefore, they can't necessarily give full sets of index buffers to VSAM clusters, and that means that there are accesses to the index component, and therefore replicate is a desirable option. Next, the buffer space parameter. Now, buffer space has to do with buffering, which we talk about later in this presentation, but it's a defined parameter. What buffer space does is it enables you to supply buffering information for the times when you're not going to supply a JCL DD statement to access your cluster. That's called an implicit access. There are several instances where this occurs. One of them is where you have an alternate index and a path built over your base cluster. When you access via the path, you can supply buffering information on the DD statement, but it only applies to the alternate index, not to the base cluster. Therefore, that base cluster should be defined with something other than minimum buffer space in order to get more than minimum buffers. Another case is where you have an alternate index with the upgrade attribute. An alternate index with the upgrade attribute will be opened and processed automatically by VSAM anytime the base cluster is updated, and that again is an implicit access with no DD statement. Therefore, again, the buffer space parameter is required to get more than minimum buffering. Final cases of this are when you use the access method services utilities dynamic allocation capabilities, and I've shown two examples here. The repro command with input data set or IDS notation and the export command. In both of those cases, a VSAM cluster is referenced by its name, but no JCL-DD statement is supplied. In these cases, if you intend to have more than the minimum amount of buffering, you have to use the buffer space parameter in your define. Something else you can do, by the way, is you can use the alter command to change the buffer space parameter. That means you don't have to go out and recreate the cluster altogether in order to change the buffer space value. Now, there's a couple of warnings that go with buffer space. First of all, if you don't code the buffer space parameter, what you get is the minimum that VSAM processing will allow, and that is 1 index buffer and 2 data buffers. The other thing to realize is something that we've mentioned earlier, and this is the real warning. Buffer space, when you specify it, can be a constraint on your control interval sizes. If the requirement up here is not met, if you've coded buffer space and control interval sizes and the values you have will not meet the requirement that buffer space can contain 1 index and 2 data buffers, then VSAM will manipulate your control interval sizes in order to satisfy that requirement, and you don't get any indication of it unless you do the listcat all that we recommended earlier. Next, let's take a look at share options. Now, this is not a presentation on VSAM sharing, but we do have a specific performance-related requirement that pertains to share option 4. Specifically, you should only use share option 4 if you know that your sharing application needs the restrictions that share option 4 introduces, because that's exactly what it does. It reduces the performance of your application by inhibiting some of VSAM's functions. With share option 4, you lose buffer look-aside for the data and index sequence set CIs. Buffer look-aside is the thing that saves VSAM I/O operations by keeping information in memory. Secondly, share option 4 will not permit you to have CA splits at all. The only exception to that is when you're using share options 4.3 in conjunction with the data facility's extended function product. And finally, with share option 4, you're not able to perform a split of the highest keyed control interval in your cluster. That is the control interval where the last record resides. Share option 4 is definitely good to avoid unless you specifically know that you need the restrictions that it introduces. Next, the speed option. Speed is something that should be specified at all times unless you have a recovery process for your initial load job. Now let's think about this for a moment. Your initial load job is the job that first puts records into your cluster sequentially. For most applications, if that job abends or fails in some way, you're going to back up and rerun the job altogether, redefine the cluster, and load the records in from the beginning. In that case, you should be using speed. Only if you have a recovery procedure that begins loading your cluster from the point of failure should you consider using recovery, because recovery has to be specified in order for a verify command to be issued against that cluster after the failure, and the verify command is necessary to determine where the logical end of the file is so that you can resume loading that cluster. Note that speed and recovery only pertain to the time you initially load a cluster, and the savings in I/O operations is only realized at initial load time. And then finally, of the processing time options, write checking. This is one of my favorites. Here we have another blanket recommendation. Don't use write check. Write check should be avoided on all DASD except possibly the 2314 if your installation is still using those. 2314s have limited error checking and correction circuitry, and therefore write checking may be desirable to verify information that has been written. On modern DASD, the 3800 series of DASD control units in particular, error checking and correction is built into the write operation. Therefore, write checking does absolutely nothing for you other than add one full rotation to every single I/O operation that you perform. Now let's take a few minutes to address execution time parameters for VSAM. What this really means is buffers, index and data buffers to be precise. We're going to look at the behavior of those buffers with sequential and direct or index search type operations and for the mixed environment, and we'll see how they're determined and specified at the time you open your VSAM cluster. First, let's make sure we understand what the minimum buffer requirements are. What's the least that you can get away with? You have to have, first of all, one index buffer for each string. Strings is a sterno parameter. Also, you have to have one data buffer per string plus one data buffer that's set aside to handle CI and CA split processing. So in mathematical terms, your buff in I value must at least equal sterno, your buff in D value must at least equal sterno plus 1. The question at this point is, how are additional buffers going to help you? First of all, in sequential processing. Sequential input processing may benefit from additional data buffers. Pay attention to the word may there, because this is not a blanket recommendation. When you have additional data buffers, sequential processing will take advantage of a function called read-ahead, which is a concept that existed way before VSAM. Read-ahead basically says read additional CIs in the first I/O operation because you're probably going to request records that come out of those control intervals. And in VSAM, it's initiated by doing a point macro or by your first sequential get for your cluster. The string that initiates this sequential processing is assigned all of the additional data buffers that there are and will do the read-ahead function all the way up to a control area boundary. Now this means there's some pretty interesting considerations in choosing data buffers for sequential processing. You have to think about it rather carefully. Looking at the general requirements, you have to have at least one additional data buffer to get any read-ahead at all. You never want to have more than a control area's worth of data buffers because read-ahead won't go beyond a control area boundary. And what's probably typical, at least as a minimum, would be 2 tracks worth. That means you have to think of your CIs in terms of physical tracks and assign at least that many buffers. One of the issues you want to consider, though, is how many CIs do you access when you make a sequential pass? If you read your whole cluster from beginning to end, then you probably want close to a half CA's worth of data buffers at least. On the other hand, if you issue a point and then read a few records and then issue a point to another location and read a few records, you're not really taking advantage of read-ahead. You don't want extensive read-ahead scheduled for your accesses because you're only getting a few records at a time and you may only need the first control interval or first 2 control intervals in a sequential stretch. That means that we have to consider carefully the choice of additional data buffers. Here's when you want to choose carefully. First of all, when you have share option 4, don't supply additional data buffers because share option 4, as we talked about earlier, disables data buffer look-aside. The read-ahead function is tied to buffer look-aside, so when you don't have any look-aside, you don't get any value out of read-ahead. Secondly, when you're using more than one string, that is a sterno value greater than 1. Since one string can dominate the entire pool of available data buffers, then essentially the other strings are lost. They only get their one data buffer and they don't get any benefits at all. And that's probably not a desirable situation. And finally, what we talked about just a moment ago, if you do short bursts or stretches of sequential retrieval at a time, you don't want extensive read-ahead because you're probably not going to use those additional data CIs. Now what about for direct processing? With VSAM, direct processing is going to benefit from additional index buffers because direct access means index searches. When you supply additional index buffers during direct processing, VSAM will use buffer look-aside to reduce I/O in the index component, specifically to the upper levels of the index, that is the index set. VSAM attempts to keep those highest index levels in core in the additional buffers. You're going to benefit from this even if you're using share option 4 and even when you have more than one string because share option 4 doesn't disable index set buffer look-aside, and with sterno greater than 1, all strings can share access to those additional index buffers. An important point to pick up here is that when we talk about index search operations, we also include the point macro. If your application issues many point macros, it's technically a sequential application, but a point means an index search, and therefore many points means supply extra index buffers to get the same performance benefit you would for a true direct application. Now, let's take a moment to refresh ourselves as to the structure of a VSAM KSDS or alternate index and make sure we understand the roles of these different levels of the index. In the diagram here we show a VSAM KSDS, very simplified diagram as a matter of fact. We have a data component composed of CAs. We have a sequence set. There's one sequence set index record per CA. And then we have the index set. That's what I sometimes refer to as the upper levels of the index. These are the additional data buffers that you would want to provide. In this rather non-realistic example, you'd want to supply 3 additional index buffers beyond sterno in order to get the benefit of the recommendation. Now that raises a question. How in the world do you determine the size of that index set? And it turns out that from a list cat all of your VSAM cluster, you can determine that index set size. Right here we illustrate an algorithm that'll do that for you. Essentially, you need to find out the rec total field from the index statistics section, high used RBA, CI size, and CIs per CA for the data component. Essentially, the logic behind this algorithm is you calculate the size of a CA, divide that into the high watermark for the cluster. That tells you how many CAs you have. The number of CAs also equals the number of sequence set records, so you subtract that number from the total number of index records, and that tells you how many records there are in the index set. That is the number of additional index buffers that you want to supply. Now finally, let's take a look at VSAM's buffer allocation scheme. If you think about it for a minute, there's a whole bunch of places where VSAM's buffering information can come from. To be precise, your program can supply buffering information in the ACB, your JCL can supply information through the AMP parameter, and the catalog can even sneak something in the buffer space parameter, which is definitely tied to buffering behavior. First thing to understand here is that the AMP parameter values will override corresponding values in the ACB. That's the opposite of non-VSAM DCB information, where the program would override a DCB specification in the JCL. With VSAM, JCL AMP takes precedence over program ACB. Once that's taken care of, VSAM next ensures that the minimum buffering requirements that we talked about are met. He sets buff_i to be equal to the larger of the current buff_i value and sterno, because there has to be one index buffer per string. Note that if buff_i wasn't specified, then a 0 participates in this, and you still end up with buff_i equals sterno. Second, for the data component, something very similar. VSAM sets buff_d equal to the larger of the current buff_d value and sterno plus 1, because the number of data buffers must at least equal the number of strings plus 1. Now, at that point, VSAM totals up how many bytes of space have been allocated. We have a calculation that looks something like this. Buff_i times index CI size plus buff_d times data CI size bytes have been allocated to buffers. At this point, VSAM compares that value to the catalog buffer space parameter. This is where the catalog buffer space comes into play. If this value is larger, that's how many buffers you get, the current buff_i and buff_d values. If the catalog buffer space value is larger, VSAM uses that as a minimum, and therefore he has some additional bytes that he can allocate. If your ACB indicates that you're performing direct processing only, VSAM adds all of the surplus bytes of buffer space as index buffs. Of course, the idea there is direct processing is going to benefit primarily from additional index buffers. If your ACB indicates anything but direct only, in other words, if it indicates sequential or skip sequential, even in combination with direct processing, VSAM first adds one index buff. That guy is dedicated towards holding the highest level index record and saving you one I/O operation per index search. Next, he takes as many bytes as there are remaining and adds as many data buffers as possible from that value. Finally, if there's bytes left over less than the size of one data buffer, VSAM will go back and again attempt to add the maximum index buffers possible from that remaining bytes of space. Of course, that's predicated on the fact that index buffers tend to be smaller than data buffers, and therefore there may be some space left over. Now, at this point, you've seen most of the material. If you're following these recommendations and you're not getting the performance you need out of your cluster, it may be time to consider some high-performance techniques. For example, you might want to take advantage of asynchronous processing. That's opcode equal ASY in the RPL. That enables you to schedule multiple RPLs at a time for I/O operations. You might want to consider control interval access. That's macref equals CNV. With control interval access, your program reads whole CIs, and it's your responsibility to extract the records from them. When you're doing control interval access, you can also perform user buffering, which allows you to allocate and manage your own I/O buffers, possibly better than VSAM. And then finally, a couple of techniques used by IBM program products. Improved CI processing, or ISIP. This is the thing that's called fast path to the IMS user. It's basically a short path in terms of CPU instructions through the VSAM I/O processor. And then finally, shared resources. LSR, which is local shared resources, and GSR, which is global shared resources. Those techniques enable you to share pools of buffers between multiple clusters, and they are a performance technique for an application that's accessing many clusters at a time. Obviously, that means online applications. This concludes our presentation on VSAM performance considerations.